Hello. Today we are going to be finishing up Chapter 10, Gas Laws, and quickly talking about diffusion and effusion. So, diffusion describes the random mixing of gases, and it is the result of the random movement because gas particles should not have strong attractions to each other, so the movement should be random. And your rate of diffusion, your rate of mixing would be increasing with temperature. And also, our smaller, less massive molecules would be diffusing faster than our larger, more massive molecules would. So, again, your particles that are going to have a lighter gram formula mass would be diffusing faster. So, with this example here, if we have a tube and HCl is introduced on one end and NH3 is introduced on the other end, they will not meet exactly in the center because their movement is going to be dependent upon their molecular mass. So obviously they're going to be at the same temperature. So whichever one is lighter will be traveling faster. So HCl is heavier, NH3 is lighter. So the NH3 is going to travel faster, and instead of meeting exactly in the center, they're going to meet closer to the HCl end. All right, effusion would be the movement of a gas into a previously empty chamber, so into a vacuum that is also dependent upon the molecular mass. So again, smaller things would be effusing faster, just like they diffused faster too. And then our final thing is real versus ideal gases. And we are usually very strong on this topic. You know, this was something that we talked about a lot in Regents chemistry. So in the real world, we have real gases. Ideal gases are ideal, and our real gases are not perfectly ideal. And our ideal gases adhere to our gas law calculations perfectly. When we have real gases, we might have some slight differences in our results due to the fact that they are not ideal. So it's important to know if something is more or less ideal because of that. So when we are at a higher temperature and a low pressure, our gases are more ideal. Your book talks about this like being on a beach vacation, but the analogy that we used in Regents chemistry was your ideal boyfriend or girlfriend. And we addressed the fact that it was a very shallow analogy, but your ideal partner was hot, low pressure, you don't want them bossing you around, and small mass. So again, very shallow. There's more things that are important than somebody's hotness or weight when determining a partner, but it works great to help us remember this analogy. So this is when they behave more with the kinetic molecular theory. So if they are smaller, they are closer to obeying that no volume clause. Also, if they are smaller, they tend to have weaker intermolecular forces, so they're closer to obeying the no intermolecular forces clause. So if we have a high temperature, low pressure, they are closer to being more ideal. High pressure, low temperature, then they are less ideal. And real gases are real and not perfectly ideal because they do have some attractions with each other. And our next unit is going to talk about intermolecular forces. So we'll touch on that some more in our next unit. But our polar molecules will be less ideal. Now, if we were being super exact, we would need to add in correction factors to the ideal gas law to account for these, but yay for us, we will not have to add in those correction factors. We just need to know when something is less ideal. So we just need to acknowledge that our results would be slightly off because we're using real gases and not ideal gases. And if we have something, a little bit heavier or with stronger intermolecular forces, then we know it would be a little bit more off. All right, so that is it for our video. Have a great day.